Hello everybody, my name is Stanislav Linchakovskyy and today I'm gonna talk about the Nobel Prize in Physics of 2005. This Nobel Prize was divided into two parts. First was given to the Roy Glauber for theory of optical coherence, and you can understand that this is theoretical physics. And our course name is Pro Seminar in Experimental Physics, so I don't gonna pay too much time to this part because we don't need to spend too much time talking about these guys. They can say this divergent integral is just constant and we don't need to pay attention to it. So the main part of report will be about John Hall and Theodor Hensch and their frequency comp. So as I said before, this prize was divided and one half awarded to the Roy Glauber for his contribution to the quantum theory of optical coherence, and the second half jointly to John Hall and Theodor Hensch for their contribution to the development of laser-based precision spectroscopy, including the optical frequency comp technique. So let's discuss what did Roy Glauber do for quantum optics. Yeah, you should understand that we start from theoretical physics part. First of all, he introduced the concept of such states that have his name, and also they called coherent states. Also, he found that the electromagnetic field is quantized and built a theoretical foundation for coherent quantum optics. Quantum optics is a very important science that found its application in lots of parts of human being. Why is it so important? We'll discuss a little bit later. Now we're gonna try to understand what Roy Glauber did. What does it mean to quantize the electromagnetic field? To do that, let us recall the solution of the problem of quantization of one-dimensional harmonic oscillator. Its Hamiltonian has the form of the first equation on this slide, and if we introduce dimensional operators, then we can get something like that, and we have that there is sum of two quadratic operators, and one is proportional to time derivative of the other. Using Maxwell equations and using Poynting vector, we can found the Hamiltonian of the electromagnetic field in form of superposition of a lot of different harmonic oscillators, as shown in the third formula on this slide. It's not that hard to understand that if the energies of the harmonic oscillator quantized, that means that the energies of the electromagnetic field is also quantized, and that's why we can talk about quantization of the electromagnetic field. If you remember that from the quantum mechanics course, we can rewrite our Hamiltonian of the harmonic oscillator using annihilation and creation operators, and the eigenstates of annihilation operators are called coherent states or Glauber states, and they have lots of different interesting properties, and the most important, I think, for these properties is that the coherent state doesn't blur in the phase space, and if the field is in the coherent state, then the uncertainty ratio is minimal. This same stuff you can, I think you have seen on the quantum mechanics course, but for the coherent states of quantum harmonic oscillator. But why these states are so important? The importance of coherent states in physics is due to the fact that in many cases physical quantized fields are in precisely such states. For example, the classical current generated by moving electric charges emit photons that are in coherent states. To make a quantum mechanical description of coherent light sources like lasers, coherent states of electromagnetic fields arise. The properties of superfluidity and superconductivity can also be explained by the fact that, respectively, the superfluid component in liquid helium and Cooper pairs in superconductors are in coherent states. That's why quantum optics and physics of coherent states found their applications, and that's why this is very important. On this slide I will stop to talk about the first part of this Nobel Prize. So you can make a brick, you can bring to your table a cup of tea, and unpause the video. So we continue. Experimental part of this Nobel Prize was given to John Hall and Theodor Hansch. And to understand what they did, let us remind two-level system. We have an atom. When it's not excited, this atom in the state of 0. If it's excited, it's in the state of 1. The energy differences of these states is delta E. And we want to talk a little bit about 3 possible types of spontaneous and force inducted and stimulated emission. So there is 3 different types how photon can interact, if I can say so, with the radiation. First type of interaction is absorption. The not excited atom interact with photon with energy delta E, for example. It's absorb this photon. The photon gives this atom all its energy, and it's rise up to the higher energetic level. The second type is spontaneous emission. I don't know if I can call it interaction, but okay. What happens during spontaneous emission? We have atom in excited state, and without any other photons, any other sources of energy, it just lowers its energy and emits a photon. Important to understand that light quanta are randomly emitted by the atoms in the form of wave packets. These wave packets are not coordinated with each other in time because it's spontaneous, yeah? And that's why these photons have a different phase. This is why spontaneous emission is incoherent. Along with spontaneous emission of an excited atom, there is a simulated or inducted or forced one. Excited atoms radiate under the action of external rapidly changed electromagnetic field such as light. It turns out that under the action of an external electromagnetic wave, the atom emits a secondary wave in which the frequency, polarization, direction of propagation, and phase completely coincide with the parameters of the external wave acting on the atom. This is a kind of copying of the external wave. The concept of stimulated emission was introduced into physics by Albert Einstein in 1916. The phenomenon of stimulated emission makes it possible to control the emission of the atoms using electromagnetic waves, and in this way generate and amplify coherent light. But to do that, we need two different things. First of all, resonance is needed. Coincidence of the frequency of the incident light with one of the frequencies of the spectrum of the atom. To be honest, very good for us that nature itself took care of the fulfillment of the resonant condition, since the emission spectra of the identical atoms are absolutely identical. Another condition is related to the population at different level. Along with stimulated emission of the light by atoms located at the upper level, resonant absorption also occurs by atoms. Whether a system of atoms will generate light or not depend on which atoms there are more in the substance. For generation to occur, it's necessary that the number of atoms at the upper level be greater than the number of atoms at the lower level, between which the transition occurs. Of course, you can use only the pair of level between which the transition is possible, because not all transition between any two levels are permitted by nature. Under natural conditions, there are fewer particles at the higher level at any temperature than at the lower level. Therefore, in any body, no matter how strongly it hit, the absorption of light will prevail over the radiation during the forced transitions. To excite the generation of coherent light, it's necessary to take special measures so that the upper one, the two chosen level, is more populated than the lower one. Thus, to excite the generation of coherent light, the population inversion is necessary for the pair of levels, the transition between which correspond to generation frequency. And the third problem that needs to be solved in order to create a laser is the problem of feedback. In order for light to control the emission of atoms, it's necessary that part of emitted light energy all the time remain inside the active medium or working substance, for reproduction causing forced emission of light with more and more and new atoms. we can done this with mirrors. Oh, sorry. We can done that with mirrors. A light wave emitted at any place as a result of spontaneous transition of an atom is amplified due to stimulated emission when it propagates through the working substance, through the active medium. Having reached the output mirror, this one, the light will partially pass through it. This part of light energy is emitted by the laser to the outside, and it can be used. Part of the light reflected from this semi-transparent output mirror give rise to new avalanche of photons, and this avalanche will not differ from the previous one due to the properties of stimulated emission. In the simple laser, each of modes, you can understand that here we have optical cavity. This is the resonator. That's why here generates lots of waves with frequency that you can get solving wave equation with boundary conditions. So frequency here is fixed, and the oscillation of the electromagnetic waves are given by these conditions. Here you can see those frequencies. Yes, in such laser, each of these modes oscillates independently, and there is no fixed relationship between each other. In essence, like a set of independent lasers, all emitting light at slightly different frequencies. The individual phase of the light waves in each mode is not fixed and may vary randomly due to such things as thermal changes in materials of lasers, for example. In lasers with only a few oscillating modes, interference between the modes can cause bidding effects in the laser's output, leading to fluctuation in intensity. In lasers with many thousands of modes, these interference effects tend to average to a near constant output intensity. If instead, if instead oscillated independently, each mode with a fixed phase between it and the other modes, the laser output behaves quite differently. Instead of random or constant output intensity, the modes of laser will periodically all constructively interfere with one another, producing an intense burst or pulse of light that you can see here. Such a laser is said to be mode locked or phased locked. These pulses occur separated in time, and this time is 1 over frequency, so it's 2L over C, because this is the time taken for the light to make exactly one round trip over the laser cavity. And this time, of course, as I said before, correspond to this frequency as reverse proportional. the duration of each pulse of light is determined by the number of modes oscillating in phase. If there are n modes locked with a frequency separation delta v, delta nu, the overall mode locked bandwidth is n delta v. Here we have. And that's how we can get the frequency comp. It's possible how we can make such synchronization of modes in the laser. For example, we can do that using Kerr effect. Let the beam intensity in a Kerr medium have a transverse, for example, Gaussian intensity distribution. Therefore, the intensity in the center of beam will be greater than in the distance from the axis of the beam moves. So after if we I'm gonna say that the greater the intensity of the beam, the stronger it will focus, and as a consequence experience less loss with distance. If these losses are properly distributed inside the laser resonator, passive mode synchronization can be obtained. So here we have frequency comp. We just used mode locking, and that's how we can have such construction. This construction is something like a ruler in the frequency space. So the formula of these lines, the frequency of these lines, is n on f repulsive plus f0. If we gonna changing f0, we can move these lines all over the spectrum, and then to use this frequency comp to, if we wanna measure some kind of spectrum, we can find the coincident of frequency of given spectrum and the frequencies in frequency comp, and using this formula we can, because here we can have something that have spectrum, for example, in radio spectrum, and we can compare it to the light spectrum and then calculate the given frequency using this formula. And this is very useful, it's very easy, because as I said before, frequency comp allows a direct link from the radio frequency standards to light frequencies, to optical frequencies. Current frequency standards, such as atomic clocks, operate in the microwave region of the spectrum, and the frequency comb brings the accuracy of such clocks into the optical part of the electromagnetic spectrum. You can understand that these comb are also using for finding the spectrums, and for example here you can see the spectrograph in the observatory. Sorry, here we have wrong captions, but no matter. And also here you can see the frequency comb that installed in these in this spectrograph. So that's all. Thank you for your attention. I hope this lecture was and will be helpful to you. Have a nice day and have a nice summer.